Hello there, AP Environmental Science class. All right, we're moving on to Chapter 17, where we're going to talk about water pollution. Now, some of the topics we're going to talk about in this chapter, we actually did touch on in other chapters. So hopefully some of the stuff you've heard of before, some of the stuff obviously going to be new. While water pollution affects all of us, obviously it's a bigger issue in underdeveloped nations, but we'll talk about how it affects not only underdeveloped nations, but developed nations as well. And the first thing we'll talk about is a core case study about the Gulf of Mexico's annual dead zone. Now, I think I did mention this in a previous lesson. Spring and summer bring huge inputs of nutrients from the Mississippi River Basin, and so you get an explosive growth of phytoplankton that eventually die and are consumed by bacteria. Well, that bacteria, as it consumes the phytoplankton, uses up a lot of oxygen. So this ends up depleting the oxygen in the Gulf of Mexico's bottom layer of water. This results in dead zones that contain little marine life. What we're going to learn is that especially larger fish, they need a decent amount of dissolved oxygen in the water to survive. So if you get rid of that dissolved oxygen, we call that a dead zone, you basically kill off all those large fish. Okay. Then what happens is in the winter storms kind of churn up the Gulf of Mexico, redistributing the oxygen, and the dead zone goes away. So you'll notice the Mississippi Basin is huge, okay? You have any rain that falls east of the Rocky Mountains or west of the Appalachian Mountains end up in the Mississippi River. And if you know, we have the Ohio River here and the Missouri River here, which are huge rivers that come from basically farmland, right? Here's the breadbasket, the Midwest, all right? We have Kansas and Nebraska here, a lot of farms. And so all these nutrients, all right, again, fertilizers used on the farms ends up growing into the Mississippi, the Ohio, the Missouri River. They all end up in the Mississippi River and then eventually end up in the Gulf of Mexico here, where again, you get these dead zones, these areas of very low dissolved oxygen that form in the summer. And again, in these areas, there's absolutely no fish. So this is a big issue for the fishermen of Louisiana, Texas, even into a little bit of Mississippi and Alabama here, okay, because they can't catch any fish during the annual dead zones in the summer, and that obviously brings issues to people who survive on catching fish, right? So a big issue. And what's interesting is that it's people far, far away from Louisiana. It's things going on in our farms in the upper Midwest and the Great Plains states that are affecting the fishermen off the Louisiana coast. Just another way to show you how environmental science, how everything is connected. You do something in one part of an area and it affects somewhere else. This is just a great example of that. Great, not in a good way, obviously, but it is a great example of how everything is connected. Something you do up here in Montana, right, in your backyard could eventually affect fishermen off the coast of Louisiana. So let's take a closer look at the Gulf of Mexico dead zone. Level of nitrates dissolved from the Mississippi River into the Gulf of Mexico has tripled since the 1950s. And again, like I told you, this causes a severe depletion in dissolved oxygen. It also is a food web disruptor, right? Because many species cannot migrate away from the area and die. Think about the seabirds and marine mammals that happen to depend on those fish and shellfish that die off. So it's not only humans. I mean, luckily we can go to the supermarket and maybe get some food. Well, that seabird can't do that. So if the fish that it normally eats dies out because of this dead zone, well, then that seabird is going to die out as well. So it also disrupts the food webs. And obviously human factors are controlling this, not only dredging and straightening of rivers, increasing the flow of nutrients coming down, but also we've removed the wetlands that act as filters for those pollutions. Remember, we talked about ecosystem services at the beginning of the year and how wetlands kind of act as a filter for us. Well, we get rid of the wetlands, we get rid of that filter, and that's what also has happened in Louisiana, down there near the Gulf of Mexico there. And so now you've even removed the filters, and therefore all those pollutants go right out into the Gulf of Mexico, producing that dead zone. So what are the causes and effects of water pollution? So the chief sources of water pollution are going to be agriculture, industry, and untreated wastewater. Untreated wastewater is basically your waste, okay? And what I mean by waste, usually talking about number one and number two, okay? And just instead of going into septic wastewater treatment plants like we have here in the U.S. In many parts of the world, that number one and number two goes right out into rivers. Okay, so and not only from us but from animals as well. Okay, so those are issues, and that's what we talk about when we talk about untreated wastewater. Okay, water pollution causes illness and death in humans and other species and disrupts ecosystems. So we're going to talk about non-point and point sources of pollution. Now, I do believe I mentioned this a little bit in a previous chapter, but we're really going to talk about it now in depth. So water pollution is any change in the water quality that can harm living organisms or make water unfit for human use. So what is a point source? A point source is a discharge of pollutants at a specific location. Examples: factories, animal feedlots, underground mines, oil wells, oil tankers. So another example would be the Indian Point power plant up here in northern Westchester. Okay, Indian Point emits hot water, which is thermal pollution, okay, out into the Hudson River. We know exactly where that hot water is coming from. It's coming from a pipe that is sticking out from underneath the Indian Point nuclear power plant right into the Hudson River where the hot water comes out. That is a point source. We know exactly where the source of the pollution is coming from. Non-point sources are more of a broad, diffuse area. Rainfall or snowmelt washes pollutants from land into surface water. Examples: runoff of fertilizers and pesticides from cropland, logged forest, lawns, and golf courses. For instance, okay, another example. We're in Ardsley. All of us put fertilizer maybe on our lawns, okay? That fertilizer eventually either seeps into the groundwater or runs off into the Sawmill River. Downriver, we sense this pollutants, okay? We don't know exactly where that pollutant came from. It could have came from your backyard. It could have came from my backyard. It could have came from someone else's backyard. We just know it's pollutants from, let's say, grass fertilizer. But we don't know exactly whose backyard the grass fertilizer pollutant came from. This is an example of a non-point source, okay? So this is what's going on. We looked at that map with the Gulf of Mexico dead zone. Most of that is non-point source pollutants. We know it's coming from farms from all over the place, right? All the fertilizer, pesticides, things like that going into the river, but we can't tell which one is coming from which individual farm. We just know it's coming from farms in general. That's your example of a non-point source of pollution. All right, so some pictures here to kind of go along with it. We'll have pictures in just a second. So the leading causes of water pollution, again, we spoke about agricultural activities, not only sediment from eroded lands when you plow and things like that, but also from fertilizers, pesticides, and bacteria from livestock and food processing waste. Then you have industrial facilities. Obviously, power plants are going to produce water pollution. Mining, we talked about that untreated human wastewater again, all right, and plastics, because plastics do not decay in water, they just float around, all right, so plastics are another leading cause of water pollution. All right, so here are some pictures. This is a point source from an industrial plant. Once again, we know exactly where the water is coming from. The pollutant is coming from. It's coming from this pipe. We know where this pipe is going into what industrial plant. This is an example of a point source pollution. Another example of a point source. This is acid draining from an abandoned open pit coal mine. All right, once again, we know where it's coming from. It's coming from this coal mine because we can see the stuff coming out of it. All right, another example of a point source. This is a non-point source. This is sediment in farmland just running off into a stream. Again, the problem is when you sample the stream and you say, okay, there's excess sediment in there. Did it come from the farm on the right? Did it come from the farm on the left? Did it come from the farm up here? Probably came from all the farms, right? But we know we can't pinpoint exactly which farm it comes from. And as a result, we call this non-point pollution or a non-point source of pollution. So again, this would be your example of that. All right, so let's understand the difference between a point and non-point source pollution. All right, if you have any issues with that, definitely come see me. So, what are some of the harmful effects of water pollutants? Well, the most serious threats to stream and lake water quality: mercury, all right, pathogens from broken sewer pipes, sediment from land disturbance and erosions, metals, and those nutrients that cause oxygen depletion. All right, these are your most serious threats to stream and lake water quality. We also have infectious disease organisms. All right, contaminated drinking water. An estimated of 1.6 million people die every year. Again, we don't see that as much in developed countries, but in underdeveloped countries, you have a lot of infectious disease organisms in water, mainly because of human and animal waste. Okay, untreated, going into water supplies, which then have these infectious diseases that cause the water to be contaminated and cause over 1.5 million people to die every year because of that. All right, so this chart here, I'm going to, the next 2 pages are kind of important. They're going to give you on the left here type and effect, so the type of a disease and the effects of it, some examples of it, and some major sources of it. So I would definitely have a few of these in mind. You may not need to memorize all the chart, but definitely pick off 2 or 3 and have a general understanding. All right, so infectious agents, pathogens, all right, caused by diseases. Examples: bacteria, viruses, protozoa, parasites. Major source going to be human and animal waste. Oxygen demanding wastes, all right, deplete dissolved oxygen needed by aquatic species. Biodegradable animal waste and plant debris. Examples of this: where do they come from? Sewage, animal feedlots, food processing facilities, paper mills. Plant nutrients, all right, cause excessive growth of algae and other species. This is your eutrophication. Nitrates, phosphates, where they come from? Sewage, animal waste, and inorganic fertilizers. Organic chemicals, all right, also problem. Add toxins to aquatic systems. Oil, gasoline, plastics, pesticides, cleaning solvents coming from an industry, farms, and households. Inorganic chemicals can also add toxins to the water systems. Acid, bases, salts, metal compounds. Where do we get those? Industry, household, surface runoff, mining sites. Sediment, right? Disrupts photosynthesis, food webs, other processes. Where does the sediment? Example of that: soil and silt. Where does it come from? Land erosion. Heavy metals can cause cancer, disrupt immune and endocrine systems. Lead, mercury, arsenic are examples. Where do they come from? Unlined landfills, household chemicals, mining refuse, industrial discharge. And again, the thermal pollution, right? Makes some species vulnerable to disease. What is that? Just heat. Electrical power, industrial plants, nuclear power plants like Indian Point. All right. So again, don't memorize all of these guys. All right. 1, 2, 3, 4, 5, 8 of them, but definitely have a couple in the back of your mind just in case you need to use it on an FRQ. All right, so what are the major pollution problems in streams and lakes? First, we'll talk about streams, then we'll go into lakes. Many streams and rivers around the world are polluted. However, streams and rivers can cleanse themselves of biodegradable waste if we do not overload them or reduce their flows. All right, this is some of the ecological services that streams and rivers provide. They can actually clean themselves, but we can't overload them with pollutants, and obviously we can't reduce their flows, because if we reduce their flows, they turn into more like lakes, and we'll talk about in a second how lakes have a hard time cleansing themselves. All right, adding excessive nutrients to lakes from human activities can disrupt ecosystems. We've talked about that. And preventing pollution is much more effective and less costly than cleaning the pollution up. So dealing with it beforehand, more effective, costs less money than actually after the pollution happens. So once again, prevention is more effective and less costly than cleanup. So in the 1970s, we started to see water pollution control laws pop up here in the U.S. A successful water cleanup project was the Cayuga River in Ohio. Believe it or not, back in the 50s and 60s, this river was on fire. Saying to yourself, how the heck can a river be on fire? Well, there was so much debris and so much pollutants floating on the top of the river that once in a while it would catch fire, and then the whole top of the river would look like it was burning because all these pollutants were actually burning on the top of the river. That's how bad it was. So obviously citizens saw this, and this cleanup was driven by bottom-up pressure from citizens who didn't want to live near a river that was on fire, because that obviously isn't what nature intended. EPA estimate: mining waste produce 40% of the headwater, pollute 40% of the headwaters of the western watershed. So out west in the U.S., 40% of the waters there are polluted because of mining, and the Ohio River is the most polluted river in the U.S., or one of them. All right, but again, since the 70s, 40, 50 years, we have had water pollution control laws. So again, you don't really hear that much about polluted rivers and streams as much in this country anymore as you may hear in some less developed countries, which we'll talk about right now. So half of the world's 500 major rivers are polluted by untreated sewage and industrial waste. Unfortunately, in our underdeveloped countries, water is most often used for human activities. So while you and I are not going to go down to the Sawmill River to get our water and to clean our clothes, in many other underdeveloped countries, that's where they go. They go to the river to take their baths, to clean their clothes, all right, to get water to drink. Nearly half of China's rivers are too toxic to touch or drink. Liver and stomach cancer linked to water pollution among the leading causes of death in China. This is not China, though. This is India. And this is Hindu people doing a daily holy ritual of washing themselves in the river. I believe this is the Ganges River, okay? What's very interesting about this, though, is they also wash their clothes and they bathe in this river. And what's also interesting is that they also discharge their human waste into this river without treating it. Not only human waste, but animal waste is discharged into this river without treating it. So you have a river that people not only use for holy rituals, but they use to clean their clothing, they bathe in it, they use the water for drinking, but they also put untreated waste into the water. Obviously, that's not a good combination because you get infectious diseases. And so these people who are using this river, unfortunately, are being, there's diseases that they could potentially get because of the fact that their river is polluted mainly from human waste and from industrial waste that is untreated and just dumped right into the river. So obviously this is a huge issue in less developed countries because this is their source of fresh water. This is where they take their baths. This is where they clean their clothes. They don't have washer machines, right? Or showers like we have in our homes. So not only are they using the river, but they're also destroying it by putting all this waste into it without treating the waste. So obviously something here needs to change. To me, don't stop your holy rituals. Don't stop bathing and cleaning yourself and drinking the river water that you've done for thousands of years. Just clean it up, okay? Don't discharge your waste without treating it into these rivers, all right? And then things will get much better. All right, we're going to talk next about something called an oxygen sag curve. This is going to be very important for you to understand, all right? It is a critical concept. So, flowing rivers or streams can dilute organic pollutants in heated water unless they're overloaded. Incidentally, that's what's going on in India, okay? Thousands of years ago, they may have still put their human waste in there, but they weren't pumping it in from people living in apartment complexes and there wasn't as many people. So the river had no problem dealing with the normal influx of human waste that was normally out there. What's happened now is with the population boom in this century or the past century going into this century, there's so many people that these rivers are getting overloaded with the human waste, with the animal waste, with the industrial waste. Again, a little bit like thousands of years ago, no problems. Okay, that's why they have a holy ritual in the river. If the river was always contaminated, I guarantee you 2,000 years ago, they wouldn't have started this. The reason why this was started is because the river used to be nice and clean. It had no problem handling the normal amount of discharge of waste. The problem is now we've overloaded these rivers, all right? And because of that, they no longer can provide the ecological service that they do or that they did to clean themselves. They can't clean themselves anymore because they're overloaded, all right? Rivers, though, do not eliminate heavy metals or slowly degradable pollutants, okay? So that's not going to be able to be cleaned up by the river itself. And an oxygen sag curve is created when degradable pollutants are emitted and bacteria act to decompose the waste. So let's take a look at this. This is going to be an important graph for you to understand. All right, what we're looking at here is basically a flowing river. All right, you'll notice the blue arrow here. So here's a point source of some type of pollution coming into the water. So above stream, no problems. Your oxygen, biochemical oxygen demand is low, stable. Your dissolved oxygen is high and stable. And so you get normal clean water organisms to live there, like trout, perch, bass, mayfly, stonefly, etc. Then what happens is we get this point source pollution that goes into the river, okay, and we get this decomposition zone. So what happens? So either bacteria come up to decompose the waste, or in some situations like eutrophication, we'll talk about in a bit, the waste, the nutrients produce an algae bloom that then the bacteria come in to decompose that algae. Regardless, the bacteria come in and they decompose what's going on here, either the pollutants or maybe the algae that has bloomed up. And those bacteria use oxygen. So now you have an influx or a blossoming of all this bacteria. So what happens? Your biochemical oxygen demand skyrockets. Okay, so now you have all this bacteria using all this oxygen. What happens to your dissolved oxygen content? Well, it begins to plummet. Here is your sag curve, okay? So you get to a point here in the septic zone where so in the decomposition zone, some pollutant tolerant fishes can survive, but a lot of fish begin to die off. Here in the septic zone, the dissolved oxygen is so low that you no longer have any fish. All you have now are anaerobic bacteria, worms, fungi, sludge, things that don't need oxygen anymore, right? Because you don't have it. The oxygen is so low. So now you have organisms that don't need oxygen. So that causes the biochemical oxygen demand to decrease. We then get into the recovery zone where, because the demand of oxygen is decreasing, the actual dissolved oxygen content is increasing. And then eventually you get back to a clean zone where normal clean water organisms can survive again. Okay, so just understand what's going on here. Again, normal clean water, high dissolved oxygen, low dissolved oxygen demand. Then you have pollutants, all right? So then you get all this bacteria that shows up to either decompose the pollutants itself or maybe decompose, let's say, an algae bloom that happens because of excess nutrients, eutrophication, right? So what happens is, once again, biochemical oxygen demand skyrockets. That causes the dissolved oxygen to decrease rather rapidly. You get to this septic zone where no fish are, nothing, no organism that need oxygen can live in here. Only anaerobic, all right, that don't need oxygen can live in here. That then reduces your oxygen demand, which will then increase the dissolved oxygen again. You get a recovery zone, and then eventually back to the clean zone where the dissolved oxygen is high and your biochemical oxygen demand is low. All right, these are your oxygen sag curves. And again, make sure you definitely understand what is going on here. All right, pollution of lakes and reservoirs. So that was just about rivers. Now we're going to talk about the pollution of lakes and reservoirs. Lakes and reservoirs are less effective at diluting pollutants than streams. Why? Because they're not moving. All right, the water is basically stationary. All right, that moving water tends to clean itself up. Stationary water doesn't. All right, so you get stratified layers with little vertical mixing. Little or no water flow, can take up to 100 years to flush and change the water in a lake. In addition, this also causes biological magnification of pollutants as the pollutants go through the food chain, okay, in that lake, because obviously we're not getting rid of the pollutants quickly like we are in a stream, all right? So this leads to that biological magnification. All right, so some terms that I know we've used before: eutrophication is the natural enrichment of a shallow lake, river mouth, or slow-moving stream caused by the runoff of plant nutrients such as nitrates and phosphates. Again, I spoke about how on the 6th hole at Spook Rock, at the golf course I play every summer, it just gets covered green with algae, all right? That is a cultural eutrophication because of the fertilizers used to make the golf course nice and green and beautiful. Those fertilizers then go into this little pond, which causes the algae to bloom because the algae loves that fertilizer. Remember, we talked about an oligotrophic lake, all right, which had low nutrients and clear water. So that is before eutrophication takes place, all right? There's not a lot of nutrients. The water is clear, but then cultural eutrophication, when nitrates and phosphates from human sources, farms, feedlots, streets, parking lots, lawns, mining sites, and sewage plants get into the water, that obviously increases the algae bloom, okay? And then what happens? The bacteria comes up to decompose that algae, and that bacteria uses all the oxygen, and this creates a dead zone in that lake or that pond. This is basically talks about what I just said. During hot weather or drought, you got dense growths of algae and cyanobacteria. Oxygen is depleted by the bacteria that decompose that algae, and then you get your oxygen sag curve to occur. Prevent or reduce cultural eutrophication, all right? So remove nitrates and phosphates from the area. Try not to use them to fertilize your lawns if you can. And recycle nutrients into the soil, not letting it run off into these ponds and into these lakes. How can we clean up lakes? Remove excess weeds, use herbicides and algicides. All right. So what do? They kill weeds and they kill algae. So you're not going to have this eutrophication to occur. Pump in air. So if you wonder why sometimes you drive around and you notice like in like a pond outside of let's say an office complex, you'll notice that there's some kind of pumping mechanism, maybe a fountain or something. Not only does it look nice, but most of the time those fountains are there to keep the water moving to stop this eutrophication, because if you have a nice little pond in front of your office complex, last thing you want to do is have that pond look all nasty and green in the summer, right? Especially if you're seeing clients, right? You want everything to be beautiful. So they throw in some of these air pumps to reduce that eutrophication from occurring. One of the not this whole on the 6th hole, there's a pond on the 10th hole at Spook Rock that actually does have one of these air things. And you'll notice in the summer, that pond stays rather clear, while the pond on the 6th hole, which doesn't have the air filter underneath it, gets totally green with that algae, with that eutrophication. Most lakes will recover if excess input of nutrients is stopped. So eventually the lakes will recover. Again, it's just a slower process than with rivers. And once again, just a picture of you. This is severe cultural eutrophication. This is Chao Lake in China. But again, I could take a picture of the pond on hole 6 at Spook Rock, or I'm sure if you drive around the area this summer, many of our smaller ponds and lakes here in Westchester have a tendency to get this cultural eutrophication because, again, of all the fertilizers, all the nutrients that we are using to keep our lawns as beautifully green as they possibly can. All right, another case study here, pollution in the Great Lakes in the 1960s. Many areas with cultural eutrophication, fish kills, and contamination in the Great Lakes. But in 1972, again, we talked about how the 70s was kind of the defining decade when it came to water pollution in the U.S. There was the Great Lakes Water Quality Agreement that was decided on. Newer upgraded sewage treatment plants around the Great Lakes. This decreased the algae blooms, which increased the dissolved oxygen levels and ended up increasing the fishing catches. So this is a success story when it comes to the pollution of the Great Lakes. If you're wondering what I'm talking about, the Great Lakes, here they are. This is the largest freshwater system in the U.S. Okay, and you'll notice Superior, Lake Michigan, Lake Huron, Lake Erie, and Lake Ontario. So bans on phosphate-containing household cleaners was also determined here, but many problems still remain. So increasing non-point runoff of pesticides and fertilizers still the greatest threat. You ever see that advertisement, Pure Michigan, right? They talk about going there to play golf and hiking and doing stuff like that. Well, obviously you're using pesticides and fertilizers to make those golf courses in Michigan look great, and then you have obviously those nutrients, those pollutants running off into the Great Lakes there. Atmospheric deposition of pesticides, mercury, and other chemicals from as far away as Mexico and Russia, right? So this is actually some of this stuff can get actually into the air and then blown. Again, everything interconnected. If this doesn't show you, I don't know what will. All right, you can get pesticides from Russia that can get into the air and can come over here with the jet stream and then can actually be deposited in the Great Lakes. 25% of the fish in the Great Lakes did have unsafe mercury content. All right, again, that gets biomagnified as you go through the food chain. So the Great Lakes Restoration Initiative, all right, was another one that was announced. This is a more recent one $1.3 billion provided between 2010 and 2015. And again, it focused on reducing toxic pollution, cultural eutrophication, loss of wildlife habitat, invasive species, and soil erosion into the lakes. And it promotes that wetland restoration. Again, wetlands, the ecological service, natural filters that help keep these pollutants out of the lakes. So it promotes those the restoration of those wetlands. That's the Great Lakes Restoration Initiative. And again, prevention approach. Call for a ban on toxic chlorine compounds used in pulp and paper industry. If we could, that would be a preventive before those toxic chlorine compounds begin to really affect the Great Lakes as well. Okay. All right. What are the major groundwater pollution problems? I think we're going to start the second part. Again, there are about 60 slides here. We did 27. I think this is a good place to drop off. So in my part 2 of my lesson on chapter 17, water pollution, we'll start talking here about groundwater pollution problems. But for that, you'll have to wait a little bit. So I'll see you for part 2.